Welcome to multiple choice question 9 of the 2010 Mathematical Methods Exam 2. In this video we will be looking at the solution for this question. A reminder that this video is in no way endorsed by VCAA. And now before we get into the question, I'd just like to point out that the use of a CAS calculator is the most efficient way to answer this question. So for question 9 we have the function f with a domain of negative infinity to a, where the rule for f of x is x cubed minus 3x squared plus 3. And we are asked, when will it have an inverse function? So an inverse function will exist provided a is one of the following options. And what we can note here is that for f inverse to exist, the original f must be 1-to-1. And more specifically, it must be 1-to-1 over this domain of negative infinity to a. So as mentioned before, the best way to tackle this problem really is to use a CAS calculator. On the CAS calculator, go into the main menu. Next, what we want to do is we want to type in the rule for f of x. So we just want the expression for it. So I'm going to have x to the power of 3 minus 3x to the power of 2 plus 3. And then we want to sketch this so that we can identify a section of the graph starting at negative infinity up until some value of a, such that it's 1-to-1. And that will mean that the inverse is also a function. So if we click on the graph icon and then drag this down, we get this cubic graph. And going analysis gsolve maximum, hitting execute will lock that point on the graph at 0, 3, and analysis gsolve minimum, which gives a minimum at 2, -1. We can see that there's a 1-to-1 section of the graph starting at negative infinity up until some value of a, and it will always be 1-to-1 as long as a is selected to be less than or equal to 0. So if we just explore that a little bit further, I'm going to clear that out. And what we'll now do to this graph is we'll just pick a restriction for it. So going back into the keyboard and math 3, I can use this straight up and down line to restrict it. And I'm going to choose the largest possible value of a. So in other words, a being 0, which was the turning point of the graph we just saw. So I'm going to sketch this graph for any x value that's less than or equal to 0. And now dragging down from the left-hand side so that we can see that that restriction's included. We've now just got part of this graph such that it's 1-to-1. So now when I go analysis sketch inverse, we can see there we have a 1-to-1 inverse function as well. So from the calculator, we saw that f of x was 1-to-1 from negative infinity up until its first turning point that occurred when x equals 0. So that means we can select any a value that's less than or equal to 0, and the function f is going to be a 1-to-1 function. So that means that a is the correct answer for this question. And just remember, what this actually means is we can choose any value of a as long as it's less than or equal to 0. So we could just as easily have graphed this for x is less than or equal to -1 or x is less than or equal to -2. Any of those restrictions would also give a 1-to-1 function, which means the inverse graph would exist. From the examiner's report, we can see that this question did challenge some students in the exam, with only 60% of students getting this question fully correct. The examiner's report also included the following commentary, which talks about solving the derivative equal to 0 to find those two stationary points which occurred at x is 0 and when x is 2, and the need for f to be 1-to-1, which we spoke about on the previous slide. The examiner also goes on to say that the answer for this particular problem could have been obtained graphically, as the x values for this particular problem of the turning points were conveniently integers. But the important thing to note here is if they hadn't have been such neat numbers to find the exact values, that's when you would have needed to solve f dash of x equal to 0 to find those values of x so that you knew where to restrict it so that the graph was 1-to-1.